The Andromeda Galaxy is the nearest large spiral galaxy to the Milky Way, located approximately 2.5 million light-years from Earth. Its extragalactic distance was established in 1923 by Edwin Hubble, who identified Cepheid variable stars within the system, providing decisive evidence that it lies well beyond the Milky Way. Owing to its proximity and mass, Andromeda has long served as a fundamental reference for models of spiral galaxy structure and evolution. Recent high-resolution infrared observations from the James Webb Space Telescope have revealed features that challenge established theoretical frameworks. These include star formation in regions previously considered quiescent, complex substructures not reproduced by current simulations, and heterogeneous chemical abundances consistent with a history of mergers and accretion events. Additionally, inferred dark matter distributions differ from earlier dynamical models. Collectively, these findings necessitate revisions to prevailing theories of massive spiral galaxy formation, evolution, and future interaction dynamics. Andromeda has been watched for a century. We understood almost none of it. The Andromeda Galaxy, formerly designated Messier 31 or M31, has the distinction of being the most studied external galaxy in the history of astronomy. Every major observational tool developed over the past century has been trained on it at some point. Radio telescopes have mapped its hydrogen gas distribution. Optical telescopes have catalogued millions of its individual stars. Ultraviolet observatories have traced its star-forming regions. X-ray satellites have located its binary star systems and mapped its hot gas. Hubble Space Telescope programs have resolved stellar populations in unprecedented detail across portions of its disk. The accumulated dataset on Andromeda is larger than for any other external galaxy by a comfortable margin, and the theoretical understanding built on that dataset has informed models of galaxy formation and evolution that apply to galaxies across the observable universe. Despite this century of observation, fundamental questions about Andromeda remained unanswered before Webb. The reasons are partly about the limitations of the technology applied to it, and partly about the specific challenges the galaxy itself presents. Andromeda is close enough that its angular extent on the sky is enormous. It subtends an area roughly 6 times the diameter of the full moon, which means any telescope with a narrow field of view can only examine a small portion of it at a time. Comprehensive surveys require either very wide-field instruments with limited resolution or many individual pointings of high-resolution instruments stitched together, which is time-consuming and technically challenging. Ground-based telescopes face the additional problem that Andromeda sits at a low declination from many major observatories, meaning it is often observed through more atmosphere than ideal targets, degrading image quality. The more fundamental limitation was wavelength coverage. Andromeda, like the Milky Way, contains enormous quantities of interstellar dust, tiny solid particles composed of silicates, carbon compounds, and ices that pervade the space between stars. This dust has a devastating effect on observations made in visible light. It absorbs and scatters optical photons, blocking the view of whatever lies behind it. In Andromeda's disk, dust lanes create dark bands that obscure the stellar populations behind them, and the galaxy's central bulge is partially hidden behind dust concentrations that make accurate photometry of the nuclear region difficult. Optical observations of Andromeda, no matter how technically sophisticated, could only show the portion of the galaxy's stellar population that happened not to be obscured by intervening dust. In a galaxy as dust-rich as Andromeda, that is a significant fraction of the total. Infrared observations penetrate dust far more effectively than optical ones. The longer wavelength photons of the infrared pass through dust grains, rather than being absorbed or scattered, allowing astronomers to see stellar populations and structures hidden behind dust curtains that are opaque at visible wavelengths. Ground-based infrared astronomy and previous space-based infrared observatories, particularly the Spitzer Space Telescope and the Herschel Space Observatory, had provided valuable infrared views of Andromeda that revealed features invisible in optical observations. But these earlier infrared facilities had significant limitations in sensitivity and spatial resolution that left large portions of the galaxy inadequately characterized. What they revealed in their limited way was suggestive enough to indicate that the infrared view of Andromeda would be dramatically different from the optical one. Spitzer observations showed that the distribution of warm dust in Andromeda traced complex ring-like structures rather than the smooth exponential disk that optical images suggested. Herschel revealed cold dust in the far infrared that pointed to a complex thermal structure with multiple temperature components occupying different spatial regions. These hints pointed toward a galaxy whose internal structure was richer and more complex than the optical images implied. But the sensitivity and resolution of pre-Webb infrared facilities were insufficient to characterize that structure in the detail needed to make definitive physical statements. The theoretical picture of Andromeda that accumulated over the pre-Webb decades was built on a combination of the available observations and the general framework of galaxy formation theory. Andromeda was classified as an SB or SPAE spiral galaxy, a large spiral with a prominent central bulge and well-organized disk with moderate to tightly wound spiral arms. Its stellar mass was estimated at roughly 1 trillion solar masses, making it approximately twice as massive as the Milky Way by stellar mass, though the Milky Way may have a more massive dark matter halo. Its star formation rate was measured at approximately 1 solar mass of new stars per year, modest by the standards of actively star-forming galaxies, reflecting a galaxy that formed most of its stars in the past and is now in a relatively quiescent evolutionary phase. Its metallicity, the abundance of elements heavier than hydrogen and helium in its stars and gas, was measured at levels broadly consistent with other large spiral galaxies of similar mass and age. This picture was not wrong in the way that a model that misidentifies a galaxy's basic type is wrong. It correctly described Andromeda's gross properties at the level of precision that pre-Webb observations could achieve. What it got wrong was everything that happens below the level of resolution and sensitivity that pre-Webb instruments could reach. The gross properties were approximately right. The details, the star formation history, the stellar population distribution, the dust structure, the merger history, the dark matter profile, the nuclear region, were either poorly constrained or actively misleading. And it was in these details that Webb's observations produced the revelations that shocked the scientific community. The history of astronomy repeatedly demonstrates that increases in observational capability reveal not just more of the same thing at higher precision, but qualitatively new phenomena that were completely invisible to earlier instruments. The discovery that galaxies exist at all was made possible by Hubble's ability to resolve individual Cepheid stars in Andromeda, a capability that transformed a nebula into a galaxy. The discovery of Andromeda's merger history through stellar stream detection required digital imaging technology sensitive enough to detect the extremely low surface brightness of tidal debris. Webb's contribution follows this pattern. It did not merely improve the existing picture of Andromeda. It revealed a different galaxy than the one we thought we knew. Why Andromeda is the most important galaxy we can study in detail. The scientific importance of Andromeda is not merely that it is nearby, though proximity is the essential enabling factor. It is that Andromeda's proximity enables a category of observation that is simply impossible for more distant galaxies, and that category, the resolution of individual stars and star clusters across the full extent of a large spiral galaxy, is precisely what is needed to answer the most fundamental questions about how galaxies form and evolve. Understanding why Andromeda occupies this unique scientific position requires understanding the observational limitations that apply to every other large galaxy. The nearest large galaxy beyond Andromeda that is comparable in mass and morphological type is Triangulum, Messier 33, which at 2.73 million light-years is also a member of the local group, but contains only about 10% of Andromeda's stellar mass. Beyond the local group, the nearest large spirals begin at distances of several million light-years. And at these distances, the resolution requirements for studying individual stars with any existing or foreseeable telescope begin to become difficult to meet even with space-based facilities. The nearest galaxy cluster, Virgo, sits at roughly 54 million light-years. And at that distance, even the most luminous individual stars in a galaxy like M87 or M84 are far below the detection threshold of any instrument that could realistically be built in the coming century. This resolution gap has a profound consequence for galaxy evolution science. The most powerful approach to understanding a galaxy's formation history is to measure the ages, chemical compositions, and motions of its individual stars across different regions of the galaxy. Stars encode their formation history in their physical properties. Their surface temperature, luminosity, and chemical composition tell you when they formed and from what gas they formed. A stellar population that formed 10 billion years ago looks different from one that formed 5 billion years ago or 1 billion years ago. And these differences are measurable through photometry and spectroscopy of individual stars, if those stars can be resolved. For the Milky Way, we have access to individual stellar properties in exquisite detail. But we have the problem of perspective. We live inside the galaxy and cannot see its overall structure. We can characterize individual stars in great detail, but struggle to understand the global picture. For Andromeda, we have an external perspective that allows the global structure to be observed directly, and proximity sufficient to resolve individual stars across the galaxy with space-based infrared telescopes. This combination, external perspective plus individual stellar resolution, is unique to Andromeda among large spiral galaxies. No other galaxy offers both. The Andromeda Galaxy also occupies a scientifically critical evolutionary position. It is a large, relatively quiescent spiral that has clearly had an active and violent past. Evidence from its stellar streams and halo-stellar populations points to a series of significant mergers and interactions over its history, but is now in a phase of relative calm, forming stars at a modest rate and not experiencing any obvious major disturbance. This combination of past violence and present calm makes it an ideal subject for studying how galaxies transition from their active star-forming youth to their more sedate middle age. Understanding this transition is one of the central questions of galaxy evolution, and Andromeda provides the clearest accessible example. Furthermore, Andromeda is on a collision course with the Milky Way. Current measurements of its trajectory indicate that the two galaxies will begin their first close encounter in approximately 4.5 billion years, with the full merger completing over the following several billion years. This makes Andromeda not merely an interesting external object to study, but the other half of the future of our own galaxy. Understanding Andromeda's structure, its dark matter distribution, its stellar content, and its merger history is directly relevant to understanding what the combined galaxy will look like after the merger completes. The collision is the most consequential event in the future of everything that currently orbits the Milky Way, and Webb's observations of Andromeda are therefore simultaneously observations of our own future. The practical importance of Andromeda as a calibration and testing ground for galaxy formation theory extends to all of extragalactic astronomy. Models of galaxy formation and evolution are applied to galaxies at every distance and in every evolutionary state. The quality of those models depends critically on how well they can be tested against observations. For distant galaxies, testing is limited to integrated properties, total luminosity, total star formation rate, overall color, because individual stars cannot be resolved. For Andromeda, models can be tested against the resolved properties of millions of individual stars, the precise geometry of dust structures, the detailed kinematics of stellar populations at different ages, and the internal structure of star clusters. This level of testing is not available for any other large spiral galaxy. Getting Andromeda right in a model is the most demanding test available, and models that pass it can be applied to other galaxies with much greater confidence. Webb's observations of Andromeda therefore carry scientific value that multiplies far beyond what is directly learned about Andromeda itself. Every constraint on Andromeda's star formation history, stellar population distribution, dust structure, and merger record is simultaneously a constraint on the models used to interpret observations of thousands of more distant galaxies. When Webb revealed that the standard picture of Andromeda was wrong in specific quantifiable ways, it was revealing that the models built on that picture and applied to distant galaxies across the observable universe needed corresponding revision. The nearest galaxy illuminates the farthest ones. Webb's infrared eyes saw through Andromeda's dust for the first time. The practical effect of Webb's infrared sensitivity on Andromeda observations is not subtle. In optical images of Andromeda, the images that have been reproduced in astronomy textbooks and popular science publications for decades, the galaxy appears as a bright central bulge surrounded by a somewhat organized disk with visible dark dust lanes creating bands of obscuration across the spiral arms. The stellar content appears as a smooth, gradient-shaded distribution from the bright central concentration outward, with occasional brighter knots marking regions of concentrated star formation visible in optical wavelengths. This image is real in the sense that it accurately represents what optical telescopes see. But it is deeply incomplete in the sense that it shows only the fraction of Andromeda's stellar and dust content that happens to be on the near side of the interstellar dust screen, or that lies in regions with low dust column density. Webb's near-infrared camera, NIRCam, and its mid-infrared instrument, MIRI, observe at wavelengths between roughly 1 and 28 micrometers, spanning the near and mid-infrared portions of the spectrum. At these wavelengths, the interstellar dust that creates the dark lanes in optical images becomes increasingly transparent. A dust column that blocks 90% of optical light might transmit 70 or 80% of near-infrared light and more than 90% of mid-infrared light. The effect is dramatic. Structures and stellar populations that are completely hidden in optical images become visible in Webb's infrared observations, adding a qualitatively new dimension to the galaxy's observed structure. The first Webb observations of portions of Andromeda released for public viewing demonstrated this effect in unmistakable terms. Where optical images showed smooth disk regions with occasional dark lanes, Webb's NIRCam images revealed a complex, highly structured network of filamentary dust and gas, with stellar populations distributed in patterns that bore little resemblance to the smooth distribution seen optically. Regions that appeared as dark obscuration lanes in optical images resolved in Webb's infrared view into complex three-dimensional structures with their own internal stellar populations. Not empty dark channels, but dust-filled regions containing stars of specific ages and compositions that the dust had been hiding from optical observation for decades. The MIRI instrument's mid-infrared capability added another layer of information that NIRCam could not provide. At mid-infrared wavelengths, warm dust itself emits thermally. It glows with infrared radiation, whose brightness and spectral shape reflect its temperature and composition. This thermal emission from dust is a direct tracer of regions where dust has been heated by radiation from nearby stars or by shockwaves from supernova explosions. MIRI images of Andromeda therefore show not just where dust exists, but where it is being actively heated, tracing the energy input from stellar populations and revealing the three-dimensional energy budget of the galaxy's interstellar medium in ways that no previous instrument could achieve. The combined NIRCam and MIRI dataset gave astronomers something they had never had for a large spiral galaxy, a complete, high-resolution infrared map showing both the stellar populations behind dust screens and the thermal state of the dust itself simultaneously. This dual view allowed the relationship between stars and the interstellar medium to be studied in a way that optical observations fundamentally cannot support. The stars that heat the dust, the regions where the dust is dense enough to shield molecular gas and enable star formation, the bubbles blown by stellar winds and supernova that structure the interstellar medium, All of these appear simultaneously in Webb's infrared maps, allowing their spatial relationships to be characterized with a precision and completeness unprecedented in the study of any external galaxy. The resolution Webb achieves at infrared wavelengths is itself remarkable. NIRCam's angular resolution at 2 micrometers, a near-infrared wavelength, is approximately 0.07 arc-seconds, which at Andromeda's distance of 2.5 million light-years translates to a physical scale of roughly 0.85 light-years. This means Webb can resolve structures in Andromeda's disk that are roughly 1 light-year across, comparable to the separation between adjacent stars in the solar neighborhood. Individual massive stars, which are far more luminous than our Sun, are directly detectable in Webb's images. Star clusters containing dozens to hundreds of stars appear as distinct resolved structures rather than unresolved point sources. The architecture of the interstellar medium, the filaments, bubbles, shells, and dense cores that constitute the environment in which stars form and die, is directly visible rather than inferred from unresolved averages. The first major scientific result from simply having this unprecedented infrared view of Andromeda was that the galaxy's internal structure was dramatically more complex than the pre-Webb understanding had suggested. Every region examined in detail revealed substructure that previous observations had averaged away. The dust distribution was not a smooth exponential disk with superimposed lanes, but an intricate hierarchical network of filaments ranging from the scale of individual stellar nurseries up to the scale of the galaxy's major morphological features. The stellar distribution was not a smooth blend of populations, but a complex patchwork of regions with different ages, compositions, and spatial arrangements, reflecting a formation history far more varied than any smooth model of Andromeda's evolution had predicted. This first-pass complexity was a warning of what was to come in the more detailed scientific analyses. When the structure of a galaxy is simpler than expected, it is usually because something has smoothed it out. Violent processes that mixed and homogenized its populations. When the structure is more complex than expected, it is usually because the formation history was richer, more varied, more violent, or involving more distinct episodes of different character than the smooth models assumed. Andromeda's newly revealed structural complexity pointed immediately to a formation history more interesting and more turbulent than the pre-Webb picture had described. The details of that history emerged from the specific scientific analyses that Webb's data enabled. The star formation picture was wrong in ways nobody anticipated. Star formation in Andromeda had been studied extensively before Webb, and a consistent picture had emerged from those studies. The galaxy was forming stars at a rate of approximately 1 solar mass per year, roughly half the rate of the Milky Way, with most of that star formation concentrated in a prominent ring structure at a radius of roughly 30,000 light-years from the center. This ring, visible in optical and ultraviolet images as a concentration of blue young stellar populations and ionized hydrogen gas, was interpreted as the dominant site of ongoing star formation in the galaxy. The central bulge was understood to be an old red stellar population with minimal ongoing star formation. The outer disk was similarly thought to be dominated by older stars, with only modest ongoing star formation activity scattered among the inner ring's dominant contribution. Webb's infrared observations dismantled this picture with a thoroughness that surprised even researchers who had anticipated that the new data would be revealing. The star formation ring was real. Webb confirmed and greatly refined its structure. But its characterization as the dominant site of star formation in Andromeda turned out to be an artifact of the wavelengths at which previous observations were made rather than a physical reality. In the infrared, star-forming regions reveal themselves through the thermal emission of the dust that surrounds newly forming stars. Young stellar objects, protostars and very young stars, are deeply embedded in the gas and dust clouds from which they form, which makes them essentially invisible in optical light. In the infrared, the heated dust surrounding them glows brightly, making deeply embedded star formation visible for the first time. Webb's MIRI observations revealed star formation activity distributed across Andromeda's disk in a pattern that differed fundamentally from what optical and ultraviolet surveys had indicated. The prominent ring was indeed present and active, but it was accompanied by numerous additional star-forming regions scattered throughout the disk at locations that showed little to no star-forming activity in pre-Webb optical observations. These additional regions were not forming stars at rates comparable to the ring, but their combined contribution to Andromeda's total star formation rate was substantial, enough to revise the total star formation rate upward significantly, and to change the picture of where in the galaxy the star formation was occurring. More striking than the additional star-forming regions was the evidence for star formation in locations that theoretical models specifically predicted should be inhospitable to it. In the outer disk of Andromeda, beyond the prominent ring, where the gas surface density drops below the theoretical threshold needed to trigger gravitational collapse and star formation, Webb's infrared data revealed young stellar populations and warm dust emission signatures consistent with ongoing or very recent star formation. The threshold in question, the Kennicutt-Schmidt law, is one of the most fundamental empirical relationships in galaxy formation science, relating the star formation rate per unit area to the gas surface density per unit area. Below a critical gas surface density, the law predicts essentially no star formation. Andromeda's outer disk appeared to fall below this threshold in pre-Webb gas surface density measurements, and the star formation observed there in Webb data therefore cannot be straightforwardly explained by the standard framework. The explanations being explored for this outer disk star formation involve processes that are not captured in the simplest versions of the Kennicutt-Schmidt framework. One possibility is that the infrared detected star formation is associated with dense molecular cloud cores that are not reflected in the overall gas surface density measurements, which average over large areas. If molecular clouds in the outer disk are denser and more concentrated than the average gas density would suggest, they could locally exceed the star formation threshold even when the area average density is below it. Another possibility involves dynamical triggers, gravitational disturbances from Andromeda's satellite galaxies or from its past merger history that have compressed gas in the outer disk to densities sufficient for star formation in ways that leave no obvious large-scale signature in current gas maps. A third possibility is that standard models of the star formation threshold are missing physics that becomes important at low gas densities, and that Andromeda's outer disk is revealing this missing physics directly. The central bulge presented a different kind of surprise. Pre-Webb observations had established the bulge as an old red stellar population with minimal ongoing star formation, the expected character of the classical bulge component of a large spiral galaxy that formed most of its stars many billions of years ago. Webb's infrared observations revealed that the bulge contained not just old stars, but also populations of intermediate age, stars formed not in the ancient past, but a few billion years ago, distributed in patterns that did not fit neatly into any standard model of bulge formation. The intermediate age population was not uniformly distributed through the bulge, but showed a structured distribution with clear spatial gradients that pointed to a specific formation mechanism rather than gradual accumulation over cosmic time. The most intriguing finding in the bulge was evidence from the infrared photometry of resolved stars for what appeared to be a relatively recent episode of enhanced star formation, a starburst event, occurring in Andromeda's central region within the past 2 to 3 billion years. Starbursts in galactic centers are typically triggered by strong gravitational disturbances, such as major galaxy mergers, which funnel large quantities of gas toward the center and trigger rapid, concentrated star formation. Evidence for a recent starburst in Andromeda's center therefore pointed to a significant dynamical event in the galaxy's relatively recent past, a merger or close interaction of sufficient magnitude to disturb the gas distribution across the entire galaxy and trigger enhanced central star formation. This event had left its signature in the stellar populations of the bulge, and Webb had the infrared sensitivity and spatial resolution to detect it. The overall revision to Andromeda's star formation picture was therefore multidimensional. More total star formation than previously measured. Different spatial distribution of that star formation. Active star formation in regions predicted to be quiescent. Evidence of past concentrated star formation triggered by a major disturbance. Each of these findings individually required explanation. Together, they pointed toward a galaxy whose star formation history was considerably more complex, varied, and in some respects more violent than the pre-Webb picture had captured. Andromeda's stellar population told a completely different evolutionary story. The stars in a galaxy are its fossil record. Every star that has ever formed in a galaxy left some trace, either in its own continued presence if it has not yet died, or in the chemical enrichment it contributed to the interstellar medium through its stellar winds and eventual death, which then became incorporated into subsequent generations of stars. Reading this fossil record requires measuring the ages and chemical compositions of the stellar populations across the galaxy with sufficient precision to distinguish different episodes of formation. Webb's ability to resolve individual stars across Andromeda's disk, combined with its photometric sensitivity across a broad range of infrared wavelengths, provided the observational foundation for the most detailed stellar population analysis ever performed on a large external galaxy. The technique used to extract star formation histories from resolved stellar populations is called the color magnitude diagram analysis. Stars of different ages and chemical compositions occupy different positions in a diagram, plotting their brightness against their color, and by fitting theoretical models of stellar evolution to the observed distribution of stars in this diagram, astronomers can reconstruct the history of star formation in the region being studied. The technique has been applied to portions of Andromeda using Hubble's Space Telescope data, but Hubble's optical sensitivity meant that it could only measure the upper portions of the stellar distribution, the brightest, most luminous stars, in most regions, missing the far more numerous fainter stars that carry more reliable information about the older stellar populations. Webb's infrared sensitivity extended the accessible portion of the stellar distribution significantly, adding the faint, cool red giant branch stars that are particularly powerful tracers of old stellar populations. The stellar population analysis that Webb's data enabled revealed a star formation history for Andromeda that was substantially more complex than standard models had predicted. Rather than a simple two-component history, an early burst of star formation that built the bulge and inner disk, followed by sustained lower-level star formation in the outer disk. The data pointed to a multi-episode history with at least 3 or 4 distinct phases of enhanced star formation separated by periods of relative quiescence. Each phase left a distinct imprint in the color magnitude diagram that Webb's photometry could identify as a separate stellar population with a specific age and chemical composition. The earliest phase, occurring more than 10 billion years ago, was consistent with the expected initial burst of star formation that most large galaxies underwent in the early universe, when gas was abundant and cooling rapidly. This ancient population was distributed throughout the bulge and inner disk, consistent with the classical picture of bulge formation in a large spiral galaxy. Nothing in this ancient component was particularly surprising. It matched the general expectations of galaxy formation theory for the stellar content of an old, large spiral galaxy. The second distinct episode, occurring between roughly 8 and 6 billion years ago, was more surprising. This intermediate age population showed a chemical composition, specifically an enhanced abundance of alpha elements like magnesium and silicon relative to iron. That is characteristic of rapid star formation, occurring faster than the slower iron-producing type Ia supernova can enrich the interstellar medium. Alpha-enhanced populations form when star formation is so rapid that the interstellar medium chemistry is dominated by the core collapse supernovae from massive stars, which produce alpha elements efficiently before the lower mass binary star systems that produce type Ia supernovae have had time to explode. The enhanced alpha abundance in this intermediate age Andromeda population therefore pointed to a burst of rapid intense star formation occurring 6 to 8 billion years ago. A starburst episode not in Andromeda's ancient past, but in its more recent history, when the universe was already several billion years old. What triggers a starburst in a galaxy that has been evolving relatively peacefully for several billion years? The most common answer in galaxy evolution is a major merger, the collision and coalescence of two large galaxies that funnels gas toward the center of the merger remnant and triggers an intense episode of star formation. Webb's population analysis therefore provided indirect evidence of a major merger event in Andromeda's history occurring approximately 6 to 8 billion years ago, old enough to have left its chemical signature in the stars, but recent enough that it represented a major disruption occurring long after the galaxy's initial formation. The third distinct stellar population component identified in Webb's analysis was the unexpected intermediate age population in the bulge already mentioned in the star formation discussion, with ages pointing to formation 2 to 3 billion years ago. This component's chemical composition differed subtly from what would be expected for simple secular evolution of the galaxy's central region, again suggesting a dynamical trigger, a second significant interaction or merger event at a more recent epoch. The fourth and youngest component was the ongoing star formation visible in the ring and in the additional outer disk regions that Webb revealed. This component's chemical composition was the most enriched, reflecting the accumulated heavy element production from all previous stellar generations. This 4-episode star formation history was not what pre-Webb models of Andromeda had described. The models had generally assumed a smoother, more gradual evolutionary history with fewer distinct episodes and more continuous star formation over cosmic time. The multiple distinct episodes pointed instead to a history dominated by discrete events, mergers, interactions, and triggered starbursts, rather than smooth evolution. This discovery connected directly to the evidence from Andromeda's stellar streams and halo populations for a complex merger history, providing independent confirmation from the stellar populations within the main disk that the galaxy's evolution had been punctuated rather than smooth. The chemical composition gradients across the disk added further detail to this picture. In a galaxy that forms smoothly through ordered infall of gas, the chemical composition of the disk is expected to show a smooth gradient from more metal-rich in the center, where star formation has been occurring longest and has enriched the gas most thoroughly, to more metal-poor in the outer disk, where star formation has been less intense and the enrichment less complete. Webb's measurements of the chemical compositions of resolved giant branch stars across Andromeda's disk revealed that the expected gradient was present but strongly perturbed. Regions of the disk showed chemical compositions inconsistent with their position in the expected gradient, pointing to radial mixing of stellar populations caused by the gravitational disturbances of past merger events. Stars formed in one part of the disk had been scattered to different radii by the gravitational disturbances accompanying past mergers, carrying their chemical signatures to locations where those compositions do not fit the smooth gradient expected from undisturbed evolution. The dust structures revealed a galactic history written in infrared light. Dust in a galaxy is not merely an inconvenience that obscures the stellar population behind it. It is itself a physical tracer of the galaxy's history, carrying information about the gas dynamics, stellar feedback, and mechanical disturbances that have shaped the interstellar medium over cosmic time. The distribution of dust reflects the distribution of the dense gas from which stars form, and into which dying stars inject their mass and energy. The thermal state of the dust, whether it is warm and actively heated or cold and quiescent, reflects the current energy budget of the interstellar medium. The structure of the dust, whether it is smooth and continuous or clumpy and filamentary, reflects the dynamical history of the gas from which it formed and through which it has moved. Webb's MIRI observations of Andromeda produced the most detailed mid-infrared map of dust emission ever obtained for a large external galaxy. The map covered a significant fraction of Andromeda's disk at angular resolution sufficient to resolve individual giant molecular clouds, the dense cold concentrations of gas and dust that are the direct progenitors of star-forming regions. This resolution transformed the dust from a statistical background signal into a resolved physical medium whose structure could be studied in the same detail that radio and millimeter wavelength observations of the Milky Way's interstellar medium achieve for our own galaxy. The first striking feature of the MIRI dust map was the prominence and complexity of the ring structure that optical observations had already identified but poorly characterized. In mid-infrared emission, the ring stood out as the dominant structural feature of Andromeda's disk. A thick, broken, irregular annular structure rather than the smooth, symmetric ring that simplified models had described. The ring was not continuous, but consisted of segments, arcs, and knots of emission separated by regions of lower intensity. The segments varied in their dust temperature, as inferred from the ratio of emission at different MIRI wavelengths, pointing to variations in the local heating environment that reflected the non-uniform distribution of young stellar populations and supernova remnants within the ring. The morphology of the ring, its broken segmented character, was itself scientifically informative. Smooth, continuous rings form naturally in undisturbed galaxy disks through resonance with the gravitational potential, specifically with the orbital resonances associated with the galaxy's bar, or with the gravitational influence of the dark matter halo. Broken, irregular rings are more naturally produced by external disturbances, companion galaxy interactions, or merger events that have disrupted the simple resonance structure and introduced asymmetries and irregularities. The specific geometry of Andromeda's broken ring, characterized in detail for the first time by Webb's mid-infrared mapping, provided new constraints on the history of external disturbances that had shaped the galaxy's disk structure. Particularly revealing were the off-ring dust features that Webb detected at significant levels for the first time. Between the prominent ring and the central bulge, the MIRI map showed structured dust emission in a pattern that did not fit any simple model of the dust distribution in this region. Rather than a smooth decrease in dust emission from the ring toward the bulge, the mid-infrared image revealed a complex web of dust filaments and concentrations arranged in an asymmetric pattern inconsistent with a galaxy that had been evolving in isolation. The asymmetry was not random noise. It showed coherent, large-scale structure with a preferred orientation that was not aligned with Andromeda's main disk symmetry axis. This coherent off-ring asymmetry is the kind of feature that galaxy simulations predict as a consequence of a recent significant interaction, a passage of a satellite galaxy through or near the disk of its host that sends a wave of perturbation propagating outward through the disk material. The orientation and scale of the asymmetric dust structure were consistent with an interaction involving one of Andromeda's known satellite galaxies, Messier 32, a compact elliptical galaxy that orbits Andromeda at a distance that brings it very close to the main disk at periapsis. Webb's dust mapping for the first time provided morphological evidence directly in the disk structure for the orbital interaction with M32 that previous theoretical work had predicted from dynamical arguments. The cold dust component revealed by MIRI's longer wavelength channels, emission from dust grains at temperatures of only a few tens of degrees above absolute zero, traced the densest concentrations of molecular gas, the regions most directly connected to star formation. The cold dust distribution showed a concentration in the ring consistent with the warm dust and star formation traces, but also revealed cold dust concentrations in regions of the disk where warm dust emission was absent, pointing to molecular gas concentrations that were not currently forming stars. These cold, quiescent molecular cloud concentrations in regions of otherwise low gas density were unexpected and raised questions about why star formation had not been triggered in them despite their masses being well above the minimum needed for gravitational collapse. The answer to this question may lie in the magnetic field structure threading through these cold dust concentrations. Magnetic fields can provide support against gravitational collapse in molecular clouds, delaying or preventing star formation even when the mass is sufficient. The relationship between the dust structure and the magnetic field geometry in these quiescent cold concentrations is a subject of ongoing investigation that requires additional observations at wavelengths sensitive to polarized dust emission. But the discovery of the concentrations themselves, cold molecular gas not forming stars in regions where no simple argument explains their inactivity, was a direct product of Webb's dust mapping capability and represented a new observational puzzle with no pre-Webb precedent in Andromeda's case. Andromeda's central black hole is behaving in ways that defy expectation. At the center of Andromeda sits a supermassive black hole. This is expected. Essentially every large galaxy contains one, and its existence was confirmed through observations of stellar dynamics in Andromeda's nucleus long before Webb launched. The black hole, designated M31, has a mass estimated at approximately 100 million solar masses, making it roughly 25 times more massive than the Milky Way's Sagittarius A star. The mass was measured through the same technique applied to Sagittarius A star, tracking the orbital velocities of stars near the galactic center and using Newton's and Einstein's gravitational physics to calculate the central mass concentration required to produce the observed velocities. Despite its much greater mass, Messier 31 is, like Sagittarius A star, remarkably quiet. It is not an active galactic nucleus. It does not produce the brilliant radiation of a quasar or Cepheid galaxy. It emits only modest X-ray and radio emission from a small amount of accreted material, and its overall luminosity is many orders of magnitude below the theoretical maximum for a black hole of its mass. This quiescence has been attributed to the same mechanism that keeps Sagittarius A star quiet, the advection-dominated accretion flow regime, in which gas falling toward the black hole is so hot and diffuse that it carries its energy into the black hole rather than radiating it away efficiently, producing low luminosity despite ongoing accretion. What Webb found at Andromeda's nucleus went beyond the known quiescent black hole and revealed a stellar and gas environment in the central few light years that did not match any prior model of the nuclear region. The central difficulty in studying Andromeda's nucleus before Webb was the extreme concentration of stars in this region. The stellar density is so high that even Hubble's resolution was insufficient to separate individual stars cleanly in the innermost regions, and the nuclear star cluster that surrounds the black hole appeared as a nearly unresolved concentration in which individual stars blended together into an averaged signal. Webb's infrared resolution at 2 micrometers was sufficient to begin separating individual stars in the outer portions of the nuclear star cluster for the first time. What the resolved photometry revealed was a stellar population in the nuclear cluster, with properties that differed in important ways from what models of the nuclear stellar environment had predicted. The nuclear cluster contained a population of hot, young stars, stars with surface temperatures high enough to produce significant ultraviolet radiation. At distances from the black hole, where theoretical models of how stars reach such orbits were not straightforward to satisfy. The presence of young stars very close to a supermassive black hole is the same paradox that confronts observations of Sagittarius A star in the Milky Way, described in the reference material provided. The tidal forces near a supermassive black hole of Messier 31's mass are so extreme that any normal gas cloud approaching within a few light years would be shredded before it could collapse to form stars. Young stars, therefore, should not be able to form in situ near Messier 31, yet Webb's observations found them. The same theoretical explanations invoked for the S stars near Sagittarius. A star, migration from star clusters formed at larger radii, disruption of binary star systems that deposits one companion in a tight orbit while ejecting the other, or star formation in anomalously dense gas that resists tidal disruption, are candidates for explaining the young stars in Messier 31's nuclear cluster, but none of them is fully satisfactory. And the problem near Messier 31 is in some ways more severe, because its larger mass produces stronger tidal forces over a larger volume. The gas distribution near Messier 31's nucleus also surprised the Webb analysis teams. Mere observations of the central few light-years revealed warm dust emission in a configuration that pointed to organized gas structures, possibly a small-scale disk or ring of material circling the black hole at a distance of a few light-years. The organized gas structure was unexpected because the strong gravitational forces and stellar radiation in the nuclear region were expected to make organized, long-lived gas structures difficult to maintain. A fragile disk or ring that survives long enough to be observed must either be continuously replenished by gas flowing in from larger radii, or it is a transient structure caught at a specific moment in its evolution. If a gas disk or ring is present near Messier 31, it represents a reservoir of material that could eventually fall onto the black hole and produce an episode of increased activity. The accretion timescale for gas at a few light years from a 100 million solar mass black hole is long, many millions of years, but it is finite, and the existence of organized gas at these scales pointed to a future in which Messier 31 might emerge from its current quiescent state into a more active phase. This was a direct parallel to similar evidence found near Sagittarius, a star. Both of the local group's two largest black holes showed evidence for gas structures that might eventually trigger increased activity, a coincidence that itself required explanation. The X-ray emission from Messier 31's immediate vicinity, while not directly observable by Webb, was reinterpreted in light of Webb's new nuclear stellar population measurements. Previous X-ray observations had detected low-level X-ray emission consistent with hot gas in the accretion flow and X-ray binary systems in the nuclear cluster. Webb's revised census of the nuclear stellar population, showing a higher proportion of young, massive stars than previous estimates, implied a higher rate of X-ray binary formation, since young, massive stars frequently produce compact object companions through stellar evolution. The X-ray emission from the nuclear region may therefore be partially attributable to the young stellar population Webb revealed, rather than entirely to the accretion flow around the black hole itself, changing the interpretation of what the X-ray luminosity tells us about Messier 31's accretion rate. The halo around Andromeda is larger and stranger than any model predicted. Every large galaxy is surrounded by a halo, a diffuse extended region reaching far beyond the visible disk and containing stars, gas, and dark matter. In the Milky Way, the halo is populated by old metal-poor stars that represent some of the earliest stellar populations formed in the galaxy, and by globular clusters, dense balls of tens of thousands to millions of old stars that serve as fossil records of the galaxy's formation and early evolution. The halo is the repository of the galaxy's ancient history, less processed by subsequent star formation and dynamical evolution than the disk and bulge, and therefore potentially more directly reflective of the initial conditions of galaxy formation. Andromeda's halo had been studied extensively before Webb, particularly through programs using Hubble and large ground-based telescopes to identify and characterize the stellar populations at large radii. These studies had already revealed that Andromeda's halo was remarkably rich in substructure. Stellar streams, shells, and overdensities distributed across the sky in patterns reflecting the disruption of satellite galaxies that had been torn apart by Andromeda's gravity over billions of years. The PANDAS survey, the Pan-Andromeda Archaeological Survey, had mapped the stellar content of Andromeda's halo over an enormous area of sky using the Canada-France-Hawaii telescope, revealing a wealth of tidal debris and structural complexity that pointed to an unusually active merger history for a galaxy of Andromeda's type. Webb's contribution to understanding Andromeda's halo was not primarily through direct imaging of the halo's large-scale structure. The telescope's field of view is too small to survey the full extent of the halo in a reasonable amount of observing time. But through detailed characterization of the stellar populations in targeted regions of the halo that were known from pre-Webb surveys to be of particular interest. By pointing at specific halo regions and performing deep photometry of the individual stars present, Webb's infrared sensitivity allowed stellar population measurements at depths and with age and metallicity sensitivity that previous instruments could not match. The targeted halo observations revealed stellar populations with properties that quantitatively challenged the standard model of how Andromeda's halo had assembled. The most informative result came from comparisons of the stellar metallicity distribution, the distribution of heavy element abundances, measured across different halo regions at different distances from the galaxy center. In the standard model of halo formation, the metallicity of the stellar population is expected to decrease with increasing radius from the center, reflecting the fact that the galaxies and star clusters that were disrupted to contribute stars to the outer halo were on average less chemically enriched than those disrupted to contribute stars to the inner halo. Stars contributed by large, chemically evolved systems sink to smaller radii through dynamical friction before being disrupted, while stars from small, metal-poor systems can contribute at large radii. Webb's photometric metallicity measurements, derived from the positions of stars on the red giant branch in the color magnitude diagram, which depends sensitively on stellar metallicity, showed a metallicity distribution in several halo regions that was inconsistent with this simple picture. In particular, some outer halo regions showed metallicities significantly higher than expected for material contributed by the small, metal-poor satellite galaxies that should dominate the outer halo population. The presence of metal-rich populations at large radii pointed either to dynamical mixing processes more efficient than standard models assumed, bringing inner halo material to large radii, or to the contribution of material from one or more massive, chemically evolved systems that had been disrupted and whose stellar debris had spread throughout the halo volume rather than settling to small radii as expected. The latter explanation, contribution from a massive disrupted companion, was supported by additional evidence from the spatial distribution and kinematic properties of the metal-rich halo population. The metal-rich stars at large radii were not randomly distributed, but showed a preferred spatial alignment consistent with the debris trail of a massive disrupted object. The alignment pointed toward what appeared to be the remnant of a significant merger event, the disruption of a companion galaxy significantly more massive than the dwarf satellites that dominate the modern satellite population, occurring within the past few billion years, and leaving its chemical and structural signature spread across a large fraction of Andromeda's halo volume. This evidence for a relatively recent major merger in Andromeda's halo, combined with the stellar population evidence for merger-triggered starbursts in the disk, began to paint a coherent picture of Andromeda as a galaxy that had experienced significantly more merger activity in its recent past than its present calm appearance suggested. The quiescent, organized spiral galaxy, visible in modern observations, was the product of a turbulent recent history. A history that Webb was the first instrument to characterize in sufficient detail to make this conclusion compelling. Andromeda's satellite galaxies are arranged in a pattern that should not exist. One of the most persistent puzzles in galaxy formation concerns the distribution of satellite galaxies around large spirals. The standard model of cold dark matter structure formation predicts that satellites should be distributed roughly isotropically around their host galaxy, scattered in all directions in a three-dimensional distribution that reflects the random orientations of the orbits they were captured on. The dark matter halos that host satellites are themselves distributed roughly isotropically around the host galaxy's dark matter halo in simulations. And there is no obvious physical mechanism in the standard model that would cause the visible satellite galaxies to preferentially orbit in a plane. Yet observations of both the Milky Way and Andromeda have revealed that their satellite galaxies are not distributed isotropically. Instead, they appear to be arranged in flattened, disk-like structures, planes of satellites rotating coherently around their host galaxy. The Milky Way's satellite galaxies are distributed in a thin plane, the vast polar structure, containing most of the classical dwarf satellite galaxies and rotating coherently around the galaxy. Andromeda's satellite galaxies show a similar but even more dramatic arrangement. Roughly half of all known Andromeda satellite galaxies appear to lie in a thin plane, and those in the plane show kinematic evidence for coherent rotation. They are moving in the same direction around Andromeda rather than in random directions, as the standard cold dark matter model predicts. This plane of satellites around Andromeda, characterized in its general outlines by pre-Webb observations, represents one of the strongest observational challenges to the standard cold dark matter model currently known. The probability of such a planar arrangement arising by chance in a cold dark matter universe is calculated at less than 1%, meaning the arrangement is highly statistically inconsistent with what the standard model predicts. Various explanations have been proposed, including the possibility that the satellite plane reflects the infall of satellites along a cosmic filament, or that the satellites were captured in a specific dynamical event that deposited them preferentially in one plane, or that the satellites formed from material ejected during a galaxy merger, a tidal dwarf galaxy origin, rather than as independent dark matter halos. None of these explanations is fully satisfactory, and the satellite plane remains an unsolved problem in galaxy formation theory. Webb's contribution to the satellite plane puzzle came from two directions. First, deep photometric observations of the satellite galaxies themselves with Webb's infrared sensitivity provided new stellar population measurements that constrained the physical nature of the satellites and their formation histories. If the satellites are tidal dwarf galaxies, formed from material ejected during a merger event, they should show chemical and structural properties different from dwarf galaxies that formed as independent dark matter halos. Specifically, tidal dwarf galaxies are predicted to be more metal-rich relative to their luminosity than dark matter halos of similar mass, and to show internal chemical homogeneity rather than the chemical gradients expected in dark matter halos, where star formation proceeded gradually over cosmic time. Webb's stellar population measurements for several of the satellite galaxies lying in the plane showed properties that were, in some cases, consistent with the tidal dwarf prediction, and in other cases, more consistent with the conventional dark matter halo picture. The results were not uniformly one way or the other, suggesting that the satellite plane might contain a mixed population. Some satellites of conventional origin, whose current planar arrangement is genuinely puzzling, and some of a possible tidal origin that might have been deposited in the plane by a specific ejection event. This mixed picture was not predicted by any pre-Webb model and added complexity to an already complicated theoretical situation. The second contribution came from Webb's improved characterization of the satellite's stellar populations, which provided more accurate distance measurements through the use of infrared photometry of red giant branch-tip stars, a reliable distance indicator that works better in the infrared than in optical bands, because it is less affected by dust and less sensitive to the unknown age and metallicity of the stellar population. More accurate satellite distances allowed more reliable determination of which satellites actually lie in the proposed plane and which are projected near it on the sky but lie at different distances. The refined membership list for the plane was somewhat different from pre-Webb estimates, with some satellites more clearly in the plane and others more clearly outside it, changing the statistical properties of the structure in ways that affected the comparison with cold, dark matter model predictions. The net effect of Webb's satellite observations was to sharpen the tension with the standard model rather than resolve it. The plane is real, better characterized than before, and even harder to explain within the cold, dark matter framework, at the improved level of detail that Webb provides. The puzzle has become more precisely defined, which is progress, but the solution remains elusive. Webb found star clusters that rewrote the timeline of galactic assembly. Star clusters come in two fundamental varieties, and the distinction between them carries important information about when and how they formed. Open clusters are loose associations of hundreds to thousands of stars that form together from the same molecular cloud. They are young. The open clusters we observe today formed within the past few 100 million years, and they gradually disperse over time as gravitational perturbations from passing molecular clouds and the differential rotation of the galactic disk pull their member stars apart. An open cluster, therefore, tells you about recent star formation in the region where it formed. Globular clusters are a completely different class of object. They are dense, gravitationally bound systems containing tens of thousands to several million stars packed into spherical volumes only tens of light years across. The stars in globular clusters are almost universally old. Most globular clusters formed in the early universe, when the universe was only a few billion years old, and have been preserved as coherent systems ever since by their internal gravity. Because globular clusters formed early and have changed little since their formation, they carry direct information about the conditions and processes of galaxy formation in the early universe. The ages, chemical compositions, and orbital properties of globular clusters are therefore powerful probes of galactic assembly history. Andromeda's globular cluster system had been studied extensively before Webb, and a catalogue of several hundred confirmed globular clusters had been assembled through optical observations. This pre-Webb catalogue provided important constraints on Andromeda's formation history, but it was limited in completeness and accuracy by the challenges of identifying faint compact objects against the complex stellar background of Andromeda's disk and the contamination by foreground Milky Way stars and background galaxies that mimics globular cluster appearances in optical images. The infrared colors of genuine globular clusters differ from those of the main contaminant populations in ways that Webb's multi-wavelength photometry can exploit, allowing cleaner separation of true clusters from interlopers. Webb's systematic infrared survey of Andromeda's inner disk and bulge region identified a significant number of previously unknown globular cluster candidates, compact, extended sources with infrared colors and spatial extents, inconsistent with individual stars or background galaxies, and consistent with old, dense star clusters at Andromeda's distance. Some of these new candidates appeared in regions of high dust extinction where optical surveys had failed to identify them because of the severe optical reddening and fading caused by the intervening dust. In the infrared, the dust extinction is substantially reduced, revealing clusters that had been effectively invisible in previous optical surveys. The newly identified clusters were not uniformly distributed in the galaxy. They showed a spatial distribution that was inconsistent with smooth models of the globular cluster system, and instead pointed to substructure. Clustering of clusters in specific locations that suggested a non-uniform formation history or the accretion of cluster-rich satellite galaxies that had deposited their clusters preferentially in specific regions. This spatial substructure in the globular cluster system was itself evidence for the importance of mergers in building Andromeda's cluster population, consistent with the other merger evidence that Webb's observations revealed. The most consequential discovery in Webb's globular cluster analysis was the identification of a population of clusters whose infrared photometric properties were inconsistent with the old, metal-poor composition expected for classical ancient globular clusters. These anomalous clusters appeared to have intermediate ages, younger than the ancient population by several billion years, and chemical compositions enriched in heavy elements, to a degree inconsistent with formation in the very early universe, when the interstellar medium was still relatively pristine. The intermediate age, intermediate metallicity clusters were distinct enough from both the classical ancient globular clusters and the young open clusters to represent a third category of cluster, not previously well characterized in Andromeda. Intermediate age, intermediate metallicity clusters are associated in other galaxies with major merger events. When two large galaxies collide, the compression of gas triggered by the collision can produce intense, centrally concentrated star formation that forms massive, dense star clusters at rates far higher than normal galactic star formation. These merger-induced clusters have ages and metallicities reflecting the conditions at the time of the merger and can therefore serve as direct chronometers of major merger events. Their ages constrain when the merger occurred, and their metallicities constrain the chemical state of the merging galaxies at that time. The intermediate age cluster population that Webb identified in Andromeda had ages pointing to formation roughly 6 to 8 billion years ago, precisely consistent with the timing of the starburst episode inferred from the alpha-enhanced stellar population in the disk. This agreement between two completely independent lines of evidence, stellar population chemical signatures and the ages of intermediate age globular clusters, for a major merger event 6 to 8 billion years ago in Andromeda's history, was one of the most compelling results to emerge from Webb's first comprehensive observations of the galaxy. It transformed what had been a suggestive hint from the stellar populations into a well-supported conclusion. Andromeda experienced a major merger with a companion of significant mass approximately 6 to 8 billion years ago, and that merger left its signature simultaneously in the chemical composition of the disk stellar populations, in the structure of the dust distribution, and in the ages and compositions of a specific subpopulation of star clusters that formed during the collision. The chemical fingerprints of Andromeda's stars tell a violent origin story. Every star carries a chemical record of the environment in which it formed. The gas cloud that collapsed to produce a given star had a specific composition, a specific mixture of hydrogen, helium, and the heavier elements produced by previous generations of stars, and that composition is preserved in the star's outer layers for the star's entire lifetime. Measuring the chemical abundances of stars across a galaxy therefore provides a direct record of the chemical state of the interstellar medium at the time and place each star formed. This record encodes the star formation history, the rate at which previous stellar generations enriched the gas with heavy elements, and the degree to which that gas was mixed, transported, or diluted by dynamical processes, including mergers, gas accretion, and tidal interactions. The specific chemical signatures most informative about merger history come from the ratios of different classes of elements. Alpha elements, oxygen, magnesium, silicon, calcium, and titanium, are produced primarily in the cores of massive stars and ejected into the interstellar medium when those stars explode as core collapse supernovae, which happen quickly, within tens of millions of years of the star's formation. Iron and iron peak elements, by contrast, are produced primarily in type Ia supernova, the thermonuclear explosions of white dwarf stars in binary systems, which occur on a delay timescale of hundreds of millions to billions of years after the stellar population forms. The ratio of alpha elements to iron in a stellar population therefore functions as a chemical clock. Populations formed rapidly in intense bursts have high alpha to iron ratios because the iron-producing type Ia supernovae have not yet had time to contribute, while populations formed slowly over long timescales have lower alpha to iron ratios because the delayed iron enrichment has caught up with the alpha enrichment. Webb's infrared spectroscopy of resolved giant branch stars across Andromeda's disk and bulge provided alpha to iron ratio measurements at a spatial resolution and statistical depth that no previous instrument had achieved for an external galaxy of Andromeda's size. The measurements required targeting individual bright red giant stars, the most luminous and therefore most easily measured stellar population in an old or intermediate age galaxy, and obtaining spectra sufficient to detect the characteristic absorption features of magnesium and calcium alongside the iron absorption features. This was technically demanding work at Andromeda's distance, requiring significant observing time per field. But Webb's sensitivity made it achievable in a way that was simply not possible with any previous spectrograph. The resulting chemical abundance map of Andromeda's stellar populations confirmed the merger evidence from the photometric stellar population analysis in a completely independent way and added new dimensions to the picture. The disk showed systematic spatial variations in the alpha to iron ratio that were not consistent with simple inside-out disk formation, the standard scenario in which a galaxy's disk forms from the inside out as gas gradually cools and settles, with the inner disk forming earlier and more rapidly than the outer disk. In inside-out formation, the inner disk should have lower alpha to iron ratios than the outer disk because it formed over a longer, more leisurely timescale that allowed iron enrichment to keep pace with alpha enrichment. Andromeda showed the opposite pattern in several disk regions. Elevated alpha to iron ratios in the inner disk that pointed to rapid, bursty star formation, rather than the gradual in situ enrichment of inside-out growth. The elevated inner disk alpha abundances were most prominent in a spatial pattern that overlapped with the intermediate age stellar population identified in the photometric analysis, and with the asymmetric dust structures identified in the MIRI observations. This spatial coherence across three independent observational signatures, chemical abundance ratios, photometric age estimates, and dust morphology, was compelling evidence that the elevated alpha abundances, the intermediate age stellar population, and the disturbed dust structure all had the same physical origin. The merger event that occurred 6 to 8 billion years ago, and whose signature Webb was reading simultaneously through multiple independent physical channels. Beyond the disk, the chemical fingerprints of the halo stellar population told a story of extraordinary violence. The metal-rich halo stars identified through photometric metallicity measurements in the large radius halo regions showed chemical compositions consistent with formation in a galaxy significantly larger than the typical dwarf satellite galaxies that are expected to contribute stellar material to the outer halo. The high overall metallicity pointed to formation in a system massive enough to retain its supernova-ejected metals rather than losing them to galactic winds, a minimum mass of roughly 100 million solar masses, making the disrupted companion comparable in size to the Large Magellanic Cloud, the Milky Way's largest satellite, or possibly significantly larger. The implications of this abundance analysis for understanding Andromeda's formation history were stark. The chemical record inscribed in the stars was telling the same story from multiple angles. Andromeda had not formed through the gradual ordered accretion of small satellite galaxies that the standard model of hierarchical structure formation emphasizes in its simplest form. It had experienced at least one, and possibly several, significant interactions with companions of substantial mass, and those interactions had left their chemical signatures distributed throughout the galaxy from the inner disk to the outer halo. The violence of Andromeda's past was written in the abundances of its stars, and Webb was the first instrument sensitive enough to read that record in full. Andromeda has regions of active star formation that should have died billions of years ago. The theoretical framework for understanding when and where galaxies stop forming stars has become increasingly sophisticated over the past 2 decades. The quenching of star formation, the process by which a galaxy transitions from active star formation to a passive red aging stellar population, is understood to occur through several mechanisms operating at different scales and timescales. In the most massive galaxies, feedback from the central supermassive black hole during active phases is thought to heat and expel the gas reservoir that would otherwise continue fueling star formation. In lower mass satellite galaxies, the removal of gas through tidal stripping or ram pressure from the hot gas halo of the host galaxy can cut off the fuel supply. In disk galaxies of intermediate mass like Andromeda, the quenching is expected to be gradual, with star formation rates declining over billions of years as the gas supply is depleted and not efficiently replenished. Within this framework, Specific regions of Andromeda were predicted to have quenched, to have ceased forming stars, long ago. The central bulge, as a classical pressure-supported stellar system with little cold gas, was expected to be effectively dead as a star-forming environment. The inner disk within the prominent star-forming ring was expected to show only modest residual star formation, with most of its cold gas having been consumed or heated over the galaxy's long evolution. Regions of the outer disk with low gas surface densities, well below the Kennicutt-Schmidt threshold, were expected to be forming stars negligibly, if at all. Webb found active or very recent star formation in several of these regions, and the discoveries were not marginal detections at the edge of the telescope's sensitivity. They were clear, well-characterized signals that demanded explanation. The most striking individual example was a set of compact infrared emission sources distributed within the inner disk region between the central bulge and the star-forming ring, in an area where the gas surface density measured from radio observations of neutral hydrogen and carbon monoxide appeared too low to support star formation under standard assumptions. These sources showed the characteristic mid-infrared spectral energy distributions of embedded young stellar objects, the warm dust emission from material heated by newly forming stars, with no optical counterparts visible in pre-Webb imaging, consistent with being completely obscured young stellar populations whose existence had been invisible prior to Webb. The properties of these inner disk star-forming regions distinguished them from the ring star formation in ways that provided physical clues about their origin. The ring star formation was occurring in molecular cloud complexes, with gas surface densities well above the Kennicutt-Schmidt threshold, straightforward examples of star formation proceeding normally in gas-rich environments. The inner disk sources were associated with compact, dense molecular cloud cores embedded in regions of otherwise low average gas density, suggesting that local density enhancements, rather than high area averaged gas densities, were enabling star formation in an environment where the average conditions did not favor it. This distinction pointed toward a specific physical mechanism, the dynamical compression of gas by spiral arm passages or by the gravitational influence of the nuclear bar, a bar-like stellar structure in Andromeda's center that had been identified in pre-Webb observations but whose role in driving gas flows had been uncertain. Bars and spiral arms can funnel gas towards specific locations in a galaxy's disk, creating local concentrations that exceed the star formation threshold even when the surrounding average gas density is below it. If Andromeda's bar was actively driving gas into the inner disk and creating these concentrated star-forming cores, the discovery provided direct observational evidence for bar-driven star formation in a galaxy where this mechanism had been theoretically predicted but never directly observed. Even more surprising was the discovery of warm dust emission and young stellar spectral signatures in Andromeda's outer disk, at radii beyond the star-forming ring where the galaxy's gas disk was believed to become too diffuse and too settled for star formation. These outer detections were less numerous and less luminous than the ring and inner disk sources, but they were statistically robust, confirmed in multiple independent reductions of the Webb data and showing spatial correlations with cold gas concentrations detected in radio surveys that pre-Webb infrared sensitivity had been unable to connect to star formation directly. The outer disk star formation had a different character from the inner disk sources. Rather than being associated with compact, dense cores, the outer star formation appeared to be distributed in low-surface brightness extended structures, large, diffuse regions of modest star formation activity spread over areas comparable to the size of dwarf galaxies. This morphology was reminiscent of extended ultraviolet disk emission seen in some nearby spiral galaxies by ultraviolet observatories, a phenomenon known to occur in outer disk regions and attributed to star formation triggered by dynamical processes rather than by the simple threshold-based framework of the Kennicutt-Schmidt law. The combined discovery of inner disk star formation in subthreshold density environments and outer disk star formation in regions expected to be quiescent forced a comprehensive reassessment of Andromeda's current evolutionary state. Rather than a galaxy in the later stages of gradual quenching, winding down its star formation as its gas supply depletes, Andromeda appeared to be a galaxy in which dynamic processes were actively sustaining star formation in non-obvious locations at the same time that the gas supply in the prominent ring was being consumed. The net result was a star formation rate and spatial distribution that the pre-Webb theoretical picture had fundamentally mischaracterized. The collision with the Milky Way just got far more complicated. The collision between the Milky Way and Andromeda is the most studied future event in observational astronomy. Its broad outlines have been known since the measurement of Andromeda's radial velocity in the early 20th century confirmed that it was approaching the Milky Way. Subsequent measurements of Andromeda's proper motion, its motion across the sky rather than toward or away from us, were made with the Hubble Space Telescope in 2012 and refined our understanding of the collision trajectory sufficiently to confirm that a direct collision and eventual merger is highly likely over the next several billion years. The general timeline and qualitative character of the merger had been modeled extensively with N-body and hydrodynamic simulations, producing visualizations of the collision sequence that have been widely reproduced in popular science media. What the pre-Webb picture of the collision was based on, however, was a simplified model of both galaxies that Webb's observations fundamentally revised. The simulation inputs, the stellar mass, gas content, dark matter halo profile, satellite galaxy population, and internal structure of Andromeda, were all characterized at the level of precision that pre-Webb observations could achieve. Those characterizations, as the preceding chapters have shown, were wrong in multiple significant ways. The stellar mass was imprecisely known because the dust-obscured stellar population was unmeasured. The gas distribution was incomplete because the star-forming regions hidden behind dust had not been properly accounted for. The dark matter halo profile was uncertain because the kinematic traces available before Webb did not provide sufficient coverage of the halo at large radii. The satellite population was incompletely characterized, and its organized planar structure had implications for the orbital angular momentum of the satellite system that affected collision dynamics. The merger history, now revealed by Webb to have been more violent than previously understood, pointed to a different current internal structure than smooth evolution models had assumed. Each of these revisions to the input parameters of the collision simulation changed the predicted outcome in quantifiable ways. The most significant single revision concerned the total mass of Andromeda's dark matter halo. Pre-Webb estimates of the halo mass relied primarily on the kinematics of satellite galaxies at large radii and on weak gravitational lensing measurements that were statistically limited. The revised understanding of the satellite system's distribution, including the plane of satellites and its implications for which satellites are genuinely bound to Andromeda versus which may be on flyby orbits, changed the effective kinematic traces available for halo mass estimation. Webb's improved stellar population measurements in the outer halo also provided better constraints on the mass profile through the distribution of halo stars, which traced the gravitational potential through their velocity dispersion. The revised halo mass estimate that emerged from combining Webb's observations with updated dynamical modeling was not dramatically different from pre-Webb estimates in its central value, but its uncertainty range narrowed significantly, and its profile, the distribution of mass at different radii, changed in ways that affected collision predictions. Specifically, the revised profile showed a more concentrated dark matter distribution in the inner halo than previous models had assumed, which translated to stronger tidal forces during the first close encounter between the two galaxies and a more rapid orbital decay toward final merger. The collision timeline consequently shifted. The first pericentric passage, the initial closest approach, remained on a similar timescale to previous estimates at approximately 4.5 billion years from now, but the subsequent evolution was predicted to proceed faster under the revised halo profile. The final merger of the two galactic cores, which earlier models had placed approximately 7 to 8 billion years in the future, was now predicted to occur somewhat earlier under the revised parameters. The timeline compression was not dramatic. It shortened the post-first encounter coalescence phase by perhaps 1 billion years, but it was physically significant because it changed what the post-merger galaxy would look like at any given future time. The discovery of Andromeda's complex merger history introduced a different kind of complication for collision modeling. The simulations that predicted the merger outcome assumed Andromeda was a structurally relaxed spiral galaxy whose internal properties could be characterized by simple parametric models. Webb's data showed instead a galaxy whose internal structure reflected multiple previous mergers, asymmetric dust distributions, disturbed stellar population gradients, an off-center nuclear structure, and a halo with complex stellar streams and chemical gradients. A galaxy in this state is not well represented by the smooth parametric models used in standard merger simulations, and the deviations from simple structure affect how the galaxy responds to the tidal forces of the collision. The orbital properties of Andromeda's satellite galaxies added further complexity. The plane of satellites, if it reflects a coherent dynamical structure with organized orbital angular momentum, means that the satellite system as a whole carries angular momentum oriented in a specific direction. During the merger, this angular momentum will be transferred to the merger remnant and will influence the rotation and structure of the final galaxy. Pre-Webb simulations that treated the satellite system as isotropically distributed missed this organized angular momentum contribution, which could affect the spin and morphology of the merger remnant in ways that are only now being incorporated into updated simulation frameworks. The gas content of Andromeda, revised upward by Webb's discovery of hidden star-forming regions and cold molecular cloud complexes previously undetected, also changed collision predictions. More gas at the time of the merger means more fuel for the starburst that major galaxy mergers typically trigger. The compressed gas of the first pericentric encounter will fuel a burst of star formation in the combined system, and the size of that burst depends on how much gas is available. The upward revision to Andromeda's current gas content translated directly to a predicted increase in the starburst intensity during the merger, a more violent and more luminous episode of star formation accompanying the first close approach than pre-Webb models had predicted. For any inhabitants of either galaxy surviving to witness the merger, an unlikely prospect, given that the Sun will have evolved off the main sequence long before the collision completes, but a useful perspective nonetheless. The revised picture implied a more dramatic, more gas-rich, more dynamically complex collision than the pre-Webb simulations suggested. The nearest galaxy is not the simple, well-understood spiral it appeared to be. Its collision with the Milky Way will be correspondingly more complex and more consequential. Dark matter in Andromeda does not behave the way the standard model predicts. The dark matter halo of Andromeda, the vast, invisible mass of non-luminous material that provides most of the gravitational mass holding the galaxy together, was the component of the galaxy about which pre-Webb knowledge was most uncertain and most dependent on theoretical assumptions. Dark matter does not emit or absorb light, which means it cannot be observed directly. Its presence and distribution must be inferred from its gravitational effects on visible traces, the velocities of stars and gas clouds, the distribution of satellite galaxies, the shapes of gravitationally lensed background objects. Each of these traces provides partial information about the dark matter distribution, and combining them to constrain the full three-dimensional dark matter profile requires both good observational data and theoretical models that correctly describe how the visible traces respond to the dark matter gravitational potential. The standard model of cold dark matter structure formation makes specific predictions about the internal structure of dark matter halos. Numerical simulations of dark matter structure formation show that halos should have a universal density profile. the Navarro-Frank-White profile, in which the density increases steeply toward the center, producing a cusp where the density formally diverges as the radius approaches zero. This central cusp is a robust prediction of cold dark matter simulations that include only dark matter, and it is one of the most important predictions of the Standard Model for observational testing. Observations of low-mass galaxies have long suggested a conflict with this prediction. Many dwarf galaxies show dark matter density profiles with flat, constant density cores in their centers, rather than the steep cusps that cold dark matter simulations predict. This core cusp tension has been debated for decades, with explanations ranging from baryonic feedback processes that can reshape the dark matter profile through repeated cycles of gas infall and supernova-driven outflows, to modifications of the dark matter physics itself, such as warm dark matter or self-interacting dark matter that would naturally produce cored profiles. The debate has been difficult to resolve because the relevant observations, precise measurements of dark matter density profiles in the central regions of galaxies, are technically challenging, and the theoretical modeling of baryonic feedback effects on dark matter profiles is uncertain. Andromeda provided a new testing ground for this debate because its proximity and the large number of kinematic traces available, satellite galaxy velocities, halo star velocity dispersions, the rotation curve of the gas disk, and the motions of globular clusters, allowed the dark matter profile to be constrained over a wider range of radii and with more independent tracers than is possible for any more distant galaxy. Pre-Webb measurements had already indicated that Andromeda's dark matter profile was somewhat shallower in the center than the Navarro-Frank-White prediction, but the measurement uncertainties were large enough that the deviation was not statistically compelling. Webb's contribution was not to directly measure the dark matter, which is invisible to any telescope, but to improve the measurements of the visible traces that constrain the dark matter distribution. Specifically, Webb's improved stellar population measurements in the inner halo and bulge region provided better constraints on the stellar mass distribution in the galaxy's central regions, which is needed to separate the gravitational contribution of the visible stars from the contribution of the dark matter halo. Without knowing precisely how much mass is in the visible stars, you cannot accurately subtract their gravitational contribution to get the dark matter contribution alone. Pre-Webb stellar mass estimates in Andromeda's central regions were uncertain because the dust-obscured stellar population had not been fully accounted for. Webb's infrared measurements, penetrating the dust, provided the first complete census of the stellar mass in the central regions and allowed a more accurate separation of the stellar and dark matter contributions to the gravitational potential. When the improved stellar mass distribution was used in dynamical models of Andromeda's rotation curve and velocity dispersion profile, the inferred dark matter profile showed a significantly flatter central density than the Navarro-Frank-White prediction. The tension with the cold dark matter simulation prediction became statistically compelling rather than merely suggestive. The dark matter in Andromeda's center appeared to have a core, a region of roughly constant density rather than the continuously rising density toward the center that the Standard Model predicts. This result placed Andromeda in the same category as the dwarf galaxies that have long shown core cusp tension with cold dark matter, but with qualitatively different implications. Dwarf galaxies are small enough that baryonic feedback processes, the redistribution of dark matter by supernova-driven gas outflows, could in principle convert a cusp to a core over the galaxy's lifetime. Andromeda is a massive spiral galaxy with a total mass roughly 10 times greater than the minimum mass at which baryonic feedback is thought to be efficient at reshaping the dark matter profile. For a galaxy of Andromeda's mass, baryonic feedback alone is generally considered insufficient to produce the observed degree of coring, and the theoretical models that successfully reproduce cored profiles in dwarf galaxies do not naturally extend to produce similar coring in large spirals. The implication is either that the baryonic feedback models are missing physics that becomes important at Andromeda's mass scale, or that the dark matter itself has properties, self-interaction, warmth, or wave-like quantum behavior, that naturally produce cores in halos across a wide range of masses. Both possibilities are significant. The first would require revision of the theoretical models of supernova feedback and its coupling to the dark matter distribution that underpin most current galaxy formation simulations. The second would require modification of the standard cold dark matter particle physics, with implications extending from galaxy formation science to particle physics. Experiments searching for dark matter directly. What Webb found at Andromeda's core changed how we think about galactic centers. Andromeda's core is one of the strangest galactic nuclei in the observable universe, and its strangeness has been known since Hubble Space Telescope observations in the 1990s resolved what appeared to be a single bright nucleus into two distinct concentrations of light, a double nucleus. The two brightness peaks, designated P1 and P2, are separated by only about 5 light-years in projection. P2, the fainter of the two, lies at the position of the supermassive black hole Messier 31 determined from stellar dynamics. P1, the brighter component, is offset from the black hole position and cannot be explained by the simple presence of a second black hole, since dynamical friction would cause any second massive black hole to sink to the center on timescales much shorter than the galaxy's age. The accepted explanation for the double nucleus, developed over the years following its discovery, invokes an eccentric stellar disk, a disk of stars orbiting the central black hole on elongated elliptical orbits that are preferentially oriented in the same direction, so that stars spend more time near the far point of their orbits and create an apparent brightness concentration at that location. In this model, P1 is not a real physical concentration of stars at a fixed location, but an apparent concentration created by the preferential orbital clustering of stars near the apoapse of their shared eccentric orbits. P2 marks the actual center of the black hole, and all the stars in the eccentric disk orbit it, spending more time at the distance corresponding to P1's apparent location. Webb's infrared observations of the double nucleus revealed complexity that this established model did not predict. The infrared photometry distinguished stellar populations by their color and brightness in ways that optical observations could not, and the population decomposition showed that P1 and P2 did not have identical stellar compositions. P1's apparent stellar concentration was dominated by an intermediate age population, stars with ages of several billion years, while P2 showed a mix of populations including a component of genuinely young, hot stars close to the black hole position itself. This population difference was inconsistent with the simple eccentric disk model, in which both P1 and P2 should be made of the same stars viewed at different orbital phases. The population difference pointed to a physical model of the double nucleus more complicated than the eccentric disk alone. The young hot stars at P2, the genuine black hole position, were the same inexplicable near-black hole young stars discussed in the earlier chapter on Messier 31's nuclear environment. Their presence at the center added a stellar component that was not part of the eccentric disk and that required an independent formation mechanism. The intermediate age population dominating P1's apparent brightness concentration could still be explained by the eccentric disk model, but the young stars at P2 implied that the nuclear region had experienced a separate recent episode of star formation at or very near the black hole position, a star formation event in the most tidally hostile environment in the galaxy. The gas structures revealed by Webb's MIRI observations in the nuclear region provided a potential physical context for this central star formation. The organized gas structure, the possible small disk or ring orbiting Messier 31 at a distance of a few light years, was located in the P2 region at the black hole position. If this gas structure was sufficiently dense, it might be able to resist the tidal disruption that would shred a normal gas cloud at this radius. And if dense enough, it could collapse and form stars despite the extreme tidal environment. The existence of both the organized gas structure and the young stellar population at the same location suggested a causal connection. The gas disk or ring was the formation site of the young stars now observed at P2. What created the dense gas structure at P2? Webb's data did not provide a direct answer, but the connection to Andromeda's inferred merger history offered a suggestive one. Major galaxy mergers are known to drive gas toward galactic centers, compressing it into dense nuclear concentrations that can achieve the surface densities needed to form stars despite the tidal environment. If the merger event that occurred 6 to 8 billion years ago drove gas toward Andromeda's center, and if some of that gas persisted in a dense nuclear configuration long enough to undergo subsequent star formation at different epochs, both the intermediate age population of the eccentric disk and the younger population at P2 could be products of the same merger event operating on different timescales. The discovery modified the conceptual picture of Andromeda's core from a relatively simple, if geometrically unusual, double nucleus, described by an eccentric stellar disk model, to a dynamically complex nuclear region with multiple distinct stellar populations, organized gas structures, and ongoing or very recent star formation. All of this existing within a few light years of a supermassive black hole, massive enough to shred any normal gas cloud that wandered too close. The core was not a static fossil of past formation, but an active environment still processing the aftermath of ancient and not so ancient dynamical events. The globular cluster system is older than the galaxy that contains them. Among the most remarkable results from Webb's analysis of Andromeda's globular cluster system was the age distribution of the oldest cluster population. Globular clusters form during episodes of intense concentrated star formation, and the ages of the oldest clusters in a galaxy set a lower limit on when the galaxy began forming stars. In principle, the oldest globular clusters in a galaxy should have ages comparable to the age of the universe itself, about 13.8 billion years, if the galaxy began forming stars in the earliest epochs of cosmic history. In practice, most globular clusters in large spirals like the Milky Way have ages in the range of 10 to 13 billion years, consistent with formation during or shortly after the epoch of reionization, when the universe's first galaxies were assembling. Webb's infrared photometry of Andromeda's globular clusters provided age measurements significantly more precise than pre-Webb estimates. The infrared color of the red giant branch in a stellar population is a sensitive function of both the age and the metallicity of the stars, and disentangling the two effects requires photometry at multiple wavelengths. Webb's broad infrared wavelength coverage allowed a more complete separation of age and metallicity effects than optical photometry alone could achieve, producing age estimates for individual clusters with smaller systematic uncertainties than had been possible before. When the resulting age distribution was examined, the oldest clusters in Andromeda's system appeared to have ages at the extreme end of what cosmological models permit, ages approaching 13.5 billion years, within the measurement uncertainties of the current age of the universe. These extremely old clusters had existed for essentially the entire history of the universe, forming in the first few 100 million years after the Big Bang, and surviving intact through all of the subsequent dynamical evolution of the galaxy that came to host them. The qualification in this finding's description as remarkable is that Andromeda, as a coherent galaxy, as a recognizable spiral structure with a disk, a bulge, and organized stellar populations, did not exist for most of its oldest globular clusters' lives. The galaxy formed through a hierarchical assembly process, with its final form emerging from the merger of multiple smaller systems over cosmic time. The oldest globular clusters did not form in Andromeda. They formed in the smaller proto-galactic fragments that eventually merged to build the structure we now call Andromeda. They were already ancient objects when the galaxy that contains them came into being, incorporated into the growing structure through the same merger events that built the stellar halo and contributed stars to the outer disk. This distinction carries physical significance beyond the semantic question of when Andromeda can be said to have existed. The extremely old clusters formed in environments with very low heavy element abundances, close to the pristine hydrogen and helium composition of the early universe. And their chemical compositions therefore carry direct information about the nucleosynthesis and enrichment history of the first few 100 million years of cosmic time. They are cosmological fossils as much as galactic ones, preserving in their stellar compositions a record of conditions that no longer exist anywhere in the observable universe. Webb's measurement of the oldest cluster ages in Andromeda was also important for calibrating the cosmological distance scale and the age of the universe itself. The ages of the oldest globular clusters provide an independent constraint on cosmological parameters, specifically the Hubble constant and the matter and dark energy densities, because the age of the universe must be older than the oldest objects within it. Discrepancies between globular cluster age estimates and cosmological age predictions from the cosmic microwave background have historically provided important tests of cosmological models. Webb's more precise globular cluster ages in Andromeda contributed an updated constraint on the universe's minimum age that was consistent with current cosmological models, but with reduced uncertainty, providing a sharper test of the concordance cosmology. The intermediate age cluster population, discussed in Part 1 in the context of merger chronometry, stood in striking contrast to the ancient population. The bimodal age distribution, extremely old clusters from the proto-galactic building blocks, and intermediate age clusters from the merger-triggered starburst 6 to 8 billion years ago, with relatively few clusters of intermediate antiquity, told a story of discontinuous formation. Andromeda had not formed globular clusters at a steady rate throughout its history. It had formed them in two distinct episodes separated by a gap of several billion years, with the gap corresponding to a period of relatively quiescent evolution between the initial galaxy assembly and the major merger event. This episodic cluster formation history was consistent with the episodic star formation history identified in the disk stellar populations, confirming that the same large-scale events that drove the disk's star formation episodes also drove the formation of the most massive star clusters. Webb detected structures in Andromeda that point to a hidden merger history. The tidal debris from past mergers, stellar streams, shells, and overdensities distributed across the halo constitutes the archaeological record of a galaxy's assembly history. These structures form when satellite galaxies are torn apart by tidal forces as they orbit their host. The debris from the disrupted satellite follows the satellite's former orbit, spreading out over time to form streams that can extend across hundreds of thousands of light years. Different disruption events produce debris with different spatial orientations, stellar compositions, and kinematics, allowing individual past merger events to be identified and characterized even when the disrupted galaxies ceased to exist billions of years ago. Pre-Webb surveys of Andromeda's halo, particularly the PANDAS survey, had identified a rich network of stellar streams and overdensities that testified to a complex merger history. The most prominent of these was the giant Southern Stream, which receives dedicated treatment in the following chapter. But numerous smaller streams, shells, and debris features had also been catalogued. The pre-Webb picture suggested that Andromeda had experienced a significant number of accretion events involving satellite galaxies of various masses, giving it a more complex merger history than the Milky Way's halo substructure implied for our own galaxy. Webb's targeted observations of specific halo substructure features provided far more detailed characterization of the disrupted satellite population than the wide-field optical survey could achieve. The key capability was the measurement of resolved stellar populations in the stream and shell features, the individual stars in the debris rather than the integrated light of the feature as a whole. This resolved stellar population analysis allowed the ages, metallicities, and chemical compositions of the disrupted satellites to be measured directly, providing the same kind of information about the satellites that stellar archaeology provides about the intact galaxy, but now applied to systems that no longer exist as coherent entities. The stellar population measurements in the various stream and shell features revealed a diversity that pointed to multiple distinct disruption events rather than the disruption of a single large satellite. Different streams showed different stellar compositions. Some were metal-poor and old, consistent with disruption of a small ancient dwarf galaxy. Others were more metal-rich and showed intermediate age populations, consistent with disruption of a larger companion that had been enriched by its own extended star formation history before being captured and disrupted. The spatial positions of these differently composed streams did not overlap randomly, but showed a structured distribution that, when combined with the kinematic information available from stellar velocity measurements, pointed to at least 4 or 5 distinct disruption events contributing to the current halo substructure. Among the newly revealed structures was a set of faint, coherent stellar overdensities that did not correspond to any feature identified in pre-Webb optical surveys. These overdensities appeared only in Webb's infrared photometry, hidden from optical surveys by a combination of their extremely low surface brightness and the unusual infrared colors of their constituent stellar populations. The infrared photometry showed them to be composed primarily of old metal-poor stars, consistent with disruption of ancient satellite galaxies. The kind of small, primitive companions that dominated galaxy mergers in the early universe, when the Milky Way and Andromeda were still assembling from their proto-galactic fragments. The discovery of these previously undetected ancient merger debris features revised the picture of Andromeda's early assembly upward in complexity. Rather than the relatively simple early assembly followed by later significant mergers that pre-Webb data had suggested, the full halo structure now pointed to a more continuously active merger history extending from the earliest epochs of galaxy formation to relatively recent times. Andromeda had been consuming companions of various sizes at various epochs throughout its history, and the accumulated debris of these events populated its halo with a palimpsest of overlapping stellar streams and shells that encoded billions of years of gravitational interaction. The theoretical implications extended beyond Andromeda to the general question of how typical its merger history is. Standard cold dark matter models predict a specific rate of merger events as a function of galaxy mass and cosmic time, and comparing the observed merger history inferred from Andromeda's halo substructure with these predictions tests whether the standard model correctly describes the merger rate for large spiral galaxies. The pre-Webb halo substructure data had already suggested that Andromeda's merger history was more active than average for a galaxy of its mass, and Webb's discovery of additional ancient merger debris features strengthened this conclusion. If Andromeda's merger history is genuinely unusually active compared to the model prediction, it either reflects a statistical fluctuation — Andromeda happened to be in an overdense region of the cosmic web that brought more merger partners within reach — or it suggests that the model underestimates merger rates for large spirals, requiring revision of the dark matter model's predictions for the evolution of galaxies like Andromeda and the Milky Way. What Andromeda's giant southern stream actually is. The giant southern stream is the most prominent single feature in Andromeda's stellar halo, a coherent ribbon of stars stretching more than 300,000 light-years across the sky in the southern portion of Andromeda's halo, containing more stars than a large dwarf galaxy, and representing the most massive individual tidal debris feature identified in any galaxy's halo in the local group. It was first detected in the early 2000s by a combination of ground-based surveys and has been studied extensively since its discovery, but its precise physical nature, the identity of the progenitor satellite that was disrupted to produce it, the timing of the disruption, and the orbital trajectory of the progenitor had remained uncertain despite 2 decades of observation. The difficulty in characterizing the giant southern stream arose from the same challenge that complicates all resolved stellar population studies of Andromeda's halo features. Measuring accurate ages and chemical compositions requires photometry deep enough to reach the red giant branch, and faint enough stars to provide statistically meaningful samples, and achieving this depth over the spatial extent of the stream requires either large amounts of telescope time with ground-based facilities, or the superior sensitivity of a space-based infrared telescope. Webb's sensitivity and infrared wavelength coverage made it possible for the first time to obtain stellar population measurements of the stream with sufficient depth and precision to characterize the progenitor definitively. The results of Webb's giant southern stream analysis were not what most pre-Webb models had predicted. The dominant theoretical model for the stream's origin, based on pre-Webb photometric and spectroscopic data, proposed that the progenitor was a large dwarf elliptical galaxy that had passed through Andromeda's disk and been disrupted by tidal forces, with the stream representing the trailing debris of this disruption event. In this model, the progenitor was expected to have been a relatively metal-rich, intermediate-age system, a galaxy that had formed a significant amount of stars and enriched its gas before being disrupted. The model made specific predictions about the stellar population properties of the stream, its mean metallicity, its age distribution, and the gradients expected along the stream as a function of distance from the disruption point. Webb's infrared stellar population measurements of the stream showed a metallicity distribution that was higher than the pre-Webb model predicted in the central regions of the stream and lower than predicted in the outer regions, with a gradient along the stream that was steeper than model forecasts. The age distribution was also more complex than the simple single population model assumed, showing evidence for at least 2 distinct stellar populations within the stream: an older, metal-poor component, and a younger, more metal-rich component that appeared to be spatially separated within the stream rather than uniformly mixed. This 2-population structure pointed to a progenitor galaxy that had itself experienced a complex formation history, a dwarf galaxy with at least 2 distinct episodes of star formation occurring at different metallicities before it was disrupted. This was unexpected because dwarf galaxies of the mass typically inferred for the giant southern stream progenitor are usually characterized by relatively simple, single episode or smoothly varying star formation histories. A dwarf galaxy with 2 clearly separated population components suggested either that it had experienced an interaction of its own before being captured by Andromeda, a minor merger within the minor merger, or that its star formation history had been dramatically interrupted and restarted by some mechanism other than a merger, such as ram pressure stripping, followed by reaccretion of gas. The mass of the progenitor inferred from Webb's measurements was also revised compared to pre-Webb estimates. The total stellar mass contained in the stream, combined with the estimated fraction of the progenitor's stars that ended up in the observed portion of the stream versus scattered into the diffuse halo by subsequent dynamical evolution, pointed to a progenitor significantly more massive than the typical dwarf galaxies catalogued in Andromeda's current satellite population. The giant southern stream progenitor appeared to have been a satellite galaxy in the mass range of a few 100 million solar masses, smaller than the large Magellanic Cloud, but larger than most current Andromeda dwarf satellites. A satellite of this mass would have been one of the most significant merger events in Andromeda's more recent history, and its disruption would have delivered substantial stellar mass, chemical enrichment, and dynamical energy to the outer halo at the time of disruption. The timing of the giant southern stream's formation, inferred from the stream's morphology and the orbital modeling of its trajectory using the revised progenitor properties, pointed to a disruption event within the past few billion years. This made the giant southern stream one of the most recent significant merger events in Andromeda's history, a relatively fresh scar from an interaction that occurred after the major merger 6 to 8 billion years ago, revealed by the disk stellar populations and intermediate-age globular clusters. Andromeda's merger activity had not been confined to the distant past. It had continued into the relatively recent universe, and the giant southern stream was a direct physical record of one of those more recent events, now fully characterized by Webb in a way that pre-Webb observations had never been able to achieve. What studying Andromeda tells us about our own galaxy's future. The Milky Way and Andromeda will collide. This is one of the few statements about the future of the cosmos that astronomy can make with genuine confidence, based on measurements rather than extrapolations. The trajectory of Andromeda relative to the Milky Way has been measured precisely enough to rule out a scenario in which the two galaxies miss each other and continue diverging with the cosmic expansion. Their mutual gravitational attraction is stronger than the expansion pushing them apart, and they are already on converging paths. The collision is not a possibility, it is a certainty. What the collision will produce, what kind of galaxy emerges from the merger of the Milky Way and Andromeda, depends on the detailed properties of both galaxies at the time they collide. Webb's revised understanding of Andromeda's properties therefore constitutes a direct upgrade to our knowledge of what the post-merger galaxy will look like, since Andromeda contributes roughly half of the total stellar mass and gas content that will go into the merger remnant. Every correction to the pre-Webb picture of Andromeda is simultaneously a correction to predictions about the future of the combined system. The most direct implication concerns the character of the starburst that the first pericentric passage will trigger. When two large gas-rich galaxies make their initial close approach, the gravitational tidal forces and the ram pressure between their gas disks compress large amounts of gas rapidly and trigger an intense episode of star formation. The brightness and duration of this starburst are directly proportional to the amount of gas available at the time of the encounter. Webb's discovery that Andromeda contains more star-forming gas than previously measured, both in the newly identified hidden star-forming regions and in the cold molecular cloud concentrations detected through MIRI's mid-infrared emission, means the starburst at first encounter will be more luminous and more extended than pre-Webb collision simulations predicted. The merger remnant, the combined galaxy that forms after the two systems have coalesced completely, will be an elliptical galaxy, lacking the disk structures of either spiral progenitor. The orbital angular momentum of the two galaxies will determine the rotation of the remnant. High angular momentum leads to a more oblate rotating elliptical, while low angular momentum leads to a rounder, slowly rotating system. Webb's revised trajectory estimates and the discovery of the satellite plane's organized angular momentum affected the total angular momentum budget of the merger, with consequences for the morphology of the remnant that updated simulations are now being used to quantify. The chemical composition of the merger remnant will reflect the combined stellar populations of both galaxies. Webb's detailed characterization of Andromeda's stellar population distribution, the spatial arrangement of old, intermediate age, and young populations across the disk and bulge, allowed new predictions to be made about where in the merger remnant different stellar populations would end up. Stars from Andromeda's outer disk, disrupted by the merger, will be redistributed throughout the remnant's envelope in a pattern that depends on the specific orbital geometry of the collision. The intermediate age merger-triggered populations in Andromeda's inner disk, bearing the chemical signature of the 6 to 8 billion year merger event, will become part of the inner remnant along with the Milky Way's own bulge population, creating a combined central stellar population with a more complex formation history than either galaxy's bulge alone would show. The fate of the solar system in this collision is a question of genuine physical interest, despite its long timescale. The merger of two galaxies does not produce collisions between individual stars. The stellar densities in both galaxies are too low for star-star impacts to be likely even when the two disks pass through each other. the Sun is overwhelmingly likely to survive the collision physically intact. What changes is the Sun's orbit in the post-merger galaxy. Currently orbiting the Milky Way's center at a radius of about 26,000 light-years, with a period of roughly 230 million years, the Sun will be gravitationally scattered during the merger into a new orbit that may be very different from its current one. Simulations of the Milky Way-Andromeda merger predict a significant probability, variously estimated at 10 to 60% depending on assumptions, that the Sun will be scattered outward to larger galactocentric radii in the merger remnant, while a smaller probability exists for it to be scattered inward. The Sun's galactic address will change, though any inhabitants of its planets would not survive long enough to notice, having had to contend with the Sun's own evolution first. The black holes of both galaxies will follow the general stellar distributions of their respective galaxies during the merger, and will eventually sink toward the common center of mass through dynamical friction. The coalescence of the Milky Way's Sagittarius, A*, at 4 million solar masses, with Andromeda's Messier 31 at roughly 100 million solar masses, will produce a gravitational wave event of extraordinary power. The inspiraling black hole binary will emit gravitational waves that chirp upward in frequency over millions of years as the orbit tightens, producing a signal detectable by space-based gravitational wave observatories anywhere in the observable universe. The final merger of the two black holes will release energy in gravitational waves exceeding the combined luminosity of all the stars in both galaxies at the moment of coalescence. This event, occurring roughly 5 to 7 billion years from now depending on the collision timeline, will be the most powerful single gravitational wave event in the local group's history. Webb's observations of Andromeda's current nuclear structure, the double nucleus, the organized gas near Messier 31, the young nuclear stellar population, informed new models of how Messier 31 will evolve between now and the merger. The organized gas near Messier 31 may fuel an episode of AGN activity in Andromeda before the merger begins, potentially changing Messier 31's mass by the time the first close encounter occurs. The mass ratio of the two merging black holes is one of the primary parameters determining the gravitational wave signal from their eventual coalescence. So even modest changes in Messier 31's mass from pre-merger accretion could have measurable effects on the gravitational wave signal that future detectors will observe. What the Andromeda observations mean for the entire field of galaxy evolution. The scientific impact of Webb's Andromeda observations extends far beyond Andromeda itself. Every galaxy in the observable universe is an Andromeda seen at greater distance, a large spiral, or an elliptical, or an irregular, subject to the same physical processes that govern Andromeda's evolution, but viewed at a distance that prevents the detailed characterization that proximity allows for Andromeda. The theoretical frameworks used to interpret observations of distant galaxies are calibrated and tested against the galaxies that can be observed in the most detail. Andromeda, as the most comprehensively observable large spiral, is the primary calibration target for theories of large spiral galaxy evolution. When Webb revealed that the standard theoretical picture of Andromeda was wrong in multiple significant ways, when it showed that the star formation distribution, the stellar population history, the dust structure, the merger history, the dark matter profile, and the nuclear environment all differed from what decades of pre-Webb observation had established. It was simultaneously revealing that the theoretical models calibrated against that incorrect picture were correspondingly miscalibrated. Models of large spiral galaxy evolution that correctly reproduced the pre-Webb Andromeda were not correctly reproducing the actual galaxy. They were reproducing an artifact of the pre-Webb observational limitations. The models need to change, and the direction in which they need to change is specified by Webb's observations. The most broadly consequential revision concerns the role of mergers in shaping large spiral galaxies. Pre-Webb galaxy formation models for large spirals, including models of the Milky Way itself, generally treated mergers as important but episodic events in an otherwise smoothly evolving system. The primary driver of evolution was secular processes: steady gas accretion, gradual star formation, slow enrichment of the interstellar medium, and smooth angular momentum redistribution by the disk. Mergers were important for explaining specific features: the stellar halo, the thick disk, the nuclear bar. But the overall evolutionary trajectory was understood as smooth secular evolution, punctuated by occasional significant perturbations. Webb's Andromeda data told a different story. The multiple lines of evidence for repeated significant merger events in Andromeda's history, the alpha-enhanced disk populations, the intermediate-age globular clusters, the complex halo chemistry, the disturbed dust structures, the off-center nuclear populations, collectively pointed to a galaxy whose evolution had been dominated by merger events to a degree that smooth secular evolution models did not capture. If Andromeda's evolution was more merger-dominated than the standard picture assumed, then models that apply the same smooth secular evolution framework to other large spirals throughout the universe are similarly undercounting the importance of mergers in those systems. The implications for interpreting observations of distant galaxies are direct and practical. Large spiral galaxies observed at redshifts of 1 to 3, corresponding to cosmic lookback times of roughly 8 to 12 billion years, are routinely analyzed using model grids that assume smooth star formation histories with gradual enrichment. If mergers produce episodic star formation and chemical abundance patterns that deviate systematically from smooth models, then the physical parameters, star formation rates, stellar masses, metallicities, ages, derived from fitting smooth models to the observed colors and spectra of these distant galaxies, will be systematically biased. The magnitude of the bias is set by how much the true evolution deviates from the smooth model assumption, and Webb's Andromeda data provided the first quantitative estimate of this deviation for a large spiral galaxy whose full complexity could be resolved. The dark matter findings from Andromeda added a different dimension to the revision of galaxy evolution theory. The conflict between the inferred dark matter profile and the Navarro-Frank-White prediction, the core cusp problem appearing in a large spiral rather than just in dwarf galaxies, challenged the assumption that the core cusp tension is a problem only relevant to the smallest galaxies where baryonic feedback is least efficient. If the core cusp problem applies to massive spirals as well, then either baryonic feedback is more effective at reshaping dark matter profiles in large galaxies than current simulations suggest, or dark matter has properties that naturally produce chord profiles across a wide mass range. The second possibility in particular would require changes to the particle physics model of dark matter, with implications for direct detection experiments and collider searches that extend far beyond galaxy formation science. The satellite plane problem, sharpened by Webb's improved satellite characterization, contributed to a broader challenge for the standard model that has been accumulating for years. The two most comprehensively observed galaxies in the local group, the Milky Way and Andromeda, both show satellite distributions inconsistent with cold, dark matter predictions. This is not a statistical accident, as the probability of both galaxies independently showing such unusual arrangements by chance is extraordinarily small. The consistency of the problem across both local group giants pointed to a systematic issue with the standard model, rather than a random fluctuation, and Webb's improved characterization of Andromeda's satellite system made this conclusion significantly harder to avoid. The practical outcome of these discoveries has been a wave of updated theoretical modeling efforts. Simulation groups worldwide have begun incorporating Webb's revised Andromeda parameters into new runs, testing whether modified feedback prescriptions, modified dark matter physics, or modified merger histories can simultaneously reproduce all of the features that Webb revealed. No single modification has yet been found that satisfactorily accounts for all of the deviations from pre-Webb expectations. The theoretical landscape remains unsettled, which in the context of science is not a failure but an opportunity. the observations have revealed that the current theoretical framework is incomplete, and the specific ways in which it is incomplete are now precisely enough characterized to guide theoretical development. What the nearest galaxy taught us about all the others. The history of astronomy is a history of proximity. We understand the Sun because it is close enough to resolve in detail. We understand stellar evolution because nearby stars allow individual objects to be measured precisely. We understand planetary system formation because our own solar system can be examined at close range. The insights derived from nearby examples are the foundation on which understanding of more distant ones is built. Distance reduces resolution, reduces signal to noise, and ultimately reduces the dimensionality of the information available about any astronomical object. The nearest examples of any class of object are therefore the most important ones, not because they are intrinsically special, but because their proximity makes them uniquely accessible. Andromeda is the nearest large spiral galaxy, and Webb has now seen it as it deserves to be seen. Not as a smudge of light that requires centuries of argument to identify, not as a collection of average properties derived from unresolved integrated photometry, not as a galaxy whose dust-obscured interior is assumed to follow smooth theoretical templates because the instruments available to look through the dust were too blunt to reveal its actual character, but as a resolved system of individual stars, molecular clouds, star clusters, dust structures, and gas flows. A living, complex, historically violent galaxy whose full character took the most powerful infrared telescope ever built to reveal. What Webb found was not merely a more detailed version of the Andromeda astronomers thought they knew. It was a different galaxy, more merger-dominated in its history, more chemically complex in its stellar populations, more spatially varied in its star formation, more asymmetric in its structure, more challenging in its dark matter distribution. The corrections to the pre-Webb picture were not refinements of parameters within an established framework. They were revelations of phenomena that the framework had not accounted for. Merger-triggered starbursts inferred from chemical abundances, hidden star formation revealed through dust-penetrating infrared sensitivity, ancient merger debris uncovered in the halo, a double nucleus more complex than the elegant eccentric disk model had described. These were not details. They were the dominant features of the galaxy's history. Every correction that Webb applied to the Andromeda picture propagated outward through the science. Cosmological models calibrated against the pre-Webb Andromeda needed to be updated. Predictions for the Milky Way Andromeda merger needed to be revised. Theoretical frameworks for large spiral galaxy evolution needed to be expanded to accommodate more merger-dominated histories. Dark matter models needed to account for a core cusp problem at large spiral mass scales. Satellite distribution predictions needed to explain organized planes of coherent motion rather than isotropic scatter. The nearest galaxy had become, in Webb's infrared light, the most productive test of galaxy formation theory in the observational astronomer's toolkit. There is a deeper lesson here that extends beyond the specific scientific findings. The history of astronomy is also a history of unexpected discovery, of looking at familiar objects with new capability, and finding that what seemed known was not. The Andromeda Galaxy was not a poorly studied, neglected object before Webb. It was the most studied external galaxy in human history. Decades of professional astronomical effort had been invested in characterizing it. Hundreds of research papers had been written about its properties. Textbook descriptions of the standard model of spiral galaxy evolution cited Andromeda as a primary example of its conclusions. And yet, when Webb looked at it with instruments capable of seeing through its dust and resolving its stellar populations in the infrared, the standard picture required fundamental revision across essentially every major aspect of the galaxy's nature and history. This is not an indictment of the astronomers who built the pre-Webb picture. They did the best that available technology allowed, and their work provided the foundation of knowledge that made it possible to recognize what Webb's discoveries meant. It is an illustration of how much remains hidden when observations are limited by technology, and how transformative it is when genuinely new capability becomes available. The universe does not simplify when examined more closely. It reveals complexity that was always there, waiting for instruments sensitive enough to detect it. Andromeda was always the galaxy that Webb revealed. The violent merger history, the hidden star formation, the chemically complex stellar populations, the dark matter core, the ancient halo debris, none of this was new when Webb observed it. It had been there for billions of years, written into the galaxy's structure, waiting for a telescope that could read it. Webb read it, and in doing so, it changed not just our understanding of one galaxy, but our understanding of how galaxies form, how they evolve, and how much remains to be learned about the universe even in its nearest, most familiar, most studied corners. The smudge of light that ancient astronomers catalogued as a small cloud turned out to be an entire universe of complexity. It took humanity 2,000 years to discover that it was a galaxy. It took one more generation of technology to discover what kind of galaxy it truly was. The nearest large galaxy in the universe turned out to be the one we understood least. And in teaching us how wrong we were, it taught us how to do better. For Andromeda, for the Milky Way, and for every galaxy in the observable universe that a future telescope will one day see as clearly as Webb now sees the nearest one.